Hello. This video is about optimization in the context of functions with several variables. We will mainly discuss extreme points, critical points, and sin. For this, we will consider the following exercise. Let n be a non-zero natural number, and let A be a real symmetric square matrix of order n. F is defined for every column vector x non-zero by f of x equals x dot x over the norm of x squared. X dot x denotes the canonical dot product of the column vectors x and x. The norm of x refers to the Euclidean norm associated with this dot product. The norm of x is the square root of x dot x. First question, show that f is bounded on Rn excluding 0 and reaches its bounds to the point that they are solutions to optimization problems. Namely, find the inf of f of x when x describes Rn 0, or the supremum of f of x when x ranges over Rn excluding 0. Second question, show that f is of class C infinity on its domain of definition and calculate its gradient at a non-zero point. Third question, show that the critical points of f are the eigenvalues of A. Fourth, calculate the sign of f at a critical point. And finally, fifth, show that the critical points of f, which are not solutions to the optimization problems mentioned above, are saddle points. We will therefore start by showing that the given function is bounded on Rn excluding 0. It is a classical function known as the Rayleigh quotient. So let's take a closer look at f. We will write f of x as ax dot x over the norm of x squared, and we express it norm in the form r applied to 1 over the norm of s dot the vector 1 over the norm of x. We have incorporated the norm into the dot product. So note that if x is in Rn 0, the vector 1 over the norm of x is normalized. It lies on the sphere S, defined by S equals the set of vectors u in Rn such that the norm of u equals 1. Conversely, any vector u from S can be written in this form: u equals 1 over the norm of x times x. It is enough to take x equal to u, which is indeed in Rn 0. Thus, we can transform the two optimization problems without constraint as follows. Finding the infimum of f of x when x describes Rn 0 is equivalent to finding the infimum of f of u when u describes the sphere S, the unit sphere S. And finding the supremum of f of x when x describes Rn 0 is equivalent to finding the supremum of f of u when u describes S. So now let's show that f is bounded on Rn 0. We will set x equal to x1, x2, xn transposed the column vector x. We denote by capital A the matrix Aij for I between 1 and n, and j between 1 and n. With this notation, f2x thus becomes f2x equals the sum for ij going from 1 to n of aij xj over the sum of xi2 for I equals 1 to n. It is enough to calculate the product ax and take the dot product with x. So in this form, f as a function of the coordinates xi is a rational function. Thus, it is continuous on its domain of definition, that is, when the norm of x is not 0, or when x is not 0. It is even C infinity. Now, regarding the fact of being bounded, we know that we are looking for the INF and the SUP on S. S is the unit sphere. It is closed, bounded, thus it is compact. And we know that a continuous function on a compact set is bounded and reaches its bounds on this compact set Therefore, our two problems have solutions. If the question is asked, secondly, show that f is of infinite class on its domain of definition and calculate its gradient at a non-zero point. So second question, f is of class C, infinite, for the same reasons as continuity, because it is a rational function in a so by it is C infinite over its domain of definition, which is Rn excluding 0, for the calculation of the gradient of f. We will calculate the first partial derivatives of fe. To calculate the first partial derivative of f with respect to xk, the coordinate xk, we will fix k between 1 and Here, of course, now we have k less than or equal to cn, and so we will write the numerator in the form for I equal to j equal to k. It will give ak kxk squared. Then the terms where there is xk, we factor out xk, and it will be the sum for I different from k, the terms ik, plus a kxi. We can group these terms because the matrix is symmetric, so we put twice sigma of a kxi. And finally, the terms that do not contain k, that means the sum for I different from k and j different from k of ijxc to facilitate differentiability or the derivation. So finally, the expression of f of x is simplified. It is a ratio of the form u over v. For the derivative, we will have uv dots minus uv over v2. Then the derivative of u with respect to xk is 2rk, kxk, plus the coefficient of xk, which is 2 stuak, x. So here, for I different from k, of course, well, we can group it into a single sigma. So it is enough to put ak, xk into the sigma and remove the I different from k. So this is u prime multiplied by v, which is the norm of x squared, minus u, we return to the form of u. Originally, it's x2 or x multiplied by the derivative of the denominator, which is 2xk, derived with respect to xk over the denominator squared, which makes the norm of x2 to the power of 4. And so the derivative of f with respect to xk e is written as 2z for y equal to 1 and 2a kxi. We have grouped these two terms. So, of course, we will divide at the top and bottom by the norm of x2. So only this term remains minus. When we divide x, scalar x, by the norm of x2, it becomes f of x, so minus 2f of x, xk, over the norm of x2 only, since we have already divided by the norm of x2. So finally, we see that the partial derivative of f with respect to xk is written twice. This sigma is none other than the fourth component of the vector x, and xk is the fourth component of the vector x. We immediately move on to the gradient of f at point x. It is 2 over the norm of x2 times the entire ax minus f of x times the entire x. Here is the expression of the gradient of f at a non-zero point x. Third question. Critical points of f are the eigenvalues of a... So we are in the third question. At this stage, if f admits a critical point at x different from 0, it means that the gradient of f is 0 at this point. But given the expression of the gradient, this means that we have x minus f of x equals 0, which precisely indicates that x is an eigenvector of A associated with the eigenvalue lambda equal to f of x. Thus, x is an eigenvector of A associated with the eigenvalue lambda equals f of x. Conversely, if we take an eigenvector of A associated with an eigenvalue lambda, we have x equals lambda x, and thus f of x. For this vector, x will be written as x dot x becomes lambda x dot x over the norm of x squared. By simplifying by the norm of x squared, we find lambda, and consequently ax minus lambda x equals 0 is equivalent to x minus f of x equals 0, which means that the gradient of f is 0 at this point, and it simply means that this point is indeed a critical point for f. Here is for the third question. Now for the fourth question, it asks to calculate the sin of f at a critical point. So fourth question, we are going to calculate the sign at point x associated with a point x associated with the eigenvalue lambda, since it is an eigenvector of A. So to calculate the sin, we will need to calculate the second order derivatives. We are not going to proceed like in the case of the gradient. We will rather use a faster method. We will set x equal to x1, x2, xn transposed. We will take h in Rn and t in R and set h equal to h1, h2, hn transposed. And we will calculate f of x plus t. This is to apply to the vector x plus t8 scalar, the vector x plus t8 over the norm of x plus t8 squared. So we develop this dot product by bilinearity. It's x to x plus tax to each plus th to x plus t to ah on the vector x plus th has component xi plus ti, thus on the norm of this vector. It's the sum from I equals 1 to n of xi plus the squared. Note that the numerator can be simplified since the products xh and ahx are equal, because the matrix A is symmetric. And so, finally, the expression where the image of x plus t8 by f becomes ax dot x plus 2t x dot h plus t squared x dot h divided by, we expand this square, so it will give sigma from I equals 1 to n of the squares of x plus 2t of the double products 2t sigma of I equals 1 and times the product x by hi plus the sum of the squares of the second term, so t squared, sigma from I equals 1 of h squared. We will provide a limited expansion of this expression with respect to 2. So obviously, to be able to do it, we will in the denominator put this term which is equal to the norm of x2 as a factor. The denominator becomes the norm of x2 as a factor of 1 plus t times this sum over the scalar product xh divided by the norm of x2 that we factored out plus then plus t squared. This is the norm of h squared divided by the norm of x squared. And we see that we have 1 plus a quantity that can be made very small if t is small enough. X and h are fixed. So we have something of the form 1 over O1 plus u. This quantity, we call it u. And we have 1 over 1 plus u, which can be written as 1 minus u plus u squared plus little O of u2. Of course, when u is small enough, or the norm of u is less than 1. So if we expand, we will have the numerator divided by the square of the norm. We will write it as its factor, 2, 1 minus u plus u2. So it will give 1 minus u minus that term. The two terms minus minus. Then plus the square of u, but we only take the square of the first term because the other exceeds the order of 2 in t, plus little o of t2. We expand and arrange according to the powers of t. So we find f of x plus 2t times x dot h over the norm of x2 minus f of x d. X dot h over the norm of x2. This is the term in t, and t2 multiplied by the remaining terms. Now note that this can be written f of x plus, we will bring the t inside the a expression, placing it next to h as th. And so it will become 2 over the norm of x2, which we factor out, times x dot th minus f of x times x dot th. We will write it as x minus f of x, x all dot. We see appearing here the gradient of f applied to the vector THE plus the rest. In the rest, we have brought TU inside. And this expression, we will identify it as follows. So, matdiki, set f2x plus th equals f2x plus gradient of f2x th plus 1.5e times its own that we are looking for applied to the scalar. So we will identify it with the expression, the development to the order, ch of f of x plus v equals f of x more the differential of f at x applied to v plus 1/2 v transpose the Hessian of f at x multiplied by v. Here, this vector is the same as the Hessian of f at x applied to v, scalar v. It should be noted that we are in a canonical basis that is orthonormal for the scalar product, and thus the two expressions are the same. So by identifying, we have the differential of f at x, which is the gradient of f of x scalar v, and in our discussion, the third important aspect that we must thoroughly examine and take into account is crucial for our understanding term will be this one, the last one that contained T2 with a 2, of course. Thus, the Hessian of f at point x, point v, scalar v, is twice this expression. So, we are asked to find the Hessian at a point x, which is a critical point. So it is an eigenvector of A associated with, let's say, the eigenvalue lambda. If that's the case, we can replace AX with lambda x. So this will become lambda x phi, thus lambda x scalar v squared. And f of x is lambda. And here we have x scalar v squared plus 4 minus 4. So the second term and the fourth cancel each other out. And thus the expression reduces to 2 over the norm of x squared times the first plus the third. That makes AV scalar v minus dot f of x norm of v squared. Here is the expression of the sin of f at a point x, which is a critical point. Last question. Show that the critical points of f, which are not solutions to the optimization problems, are above, that is to say, the inf and the sub of f are saddle points. So for this, we will thus recall that A is a symmetric matrix. Let's order the eigenvalues in this order, lambda 1, lambda 2, lambda n. Recall that the critical points of f are the eigenvectors of A. So we have an eigenvector of A, f of multiple x, f of non-x is equal to lambda, and thus the minimum. The INF of f of x will be lambda 1, and the max of f of x will be lambda n. So if X is a critical point associated with the eigenvalue lambda and is not a solution to the optimization problems, this means that the lambda or the eigenvalue associated with X is different from lambda and lambda since it is not a solution to either the INF or the SUBO. Or in other words, lambda is strictly between lambda 1 and lambda 1. Then obviously, when we calculate the expression of the ASN in V scalar V, then we obtain 2 over the norm of X squared AV, scalar V minus f of X norm of V squared, to show that at a point X, which is not an extremum, at that point F presents a saddle point, it is necessary to show that its sign changes. So if we are at a point X, which is a critical point, it will be associated with an eigenvalue, lambda, since it is a vector, eigen of A. In this case, S1 at this point will be written as 2 over the norm of X squared, AV scalar V minus lambda lambda CF of X norm of V squared, showing that it changes sign. If we take for V an eigenvector associated with lambda, the smallest of the eigenvalues, in this case, the expression will be written V is associated with lambda in AV. It's lambda 1V. This quantity becomes lambda, norm of V squared. So here it is written as lambda minus lambda, norm of V squared, with a coefficient 2 on lambda x2. Since lambda is strictly less than lambda, this quantity is negative. But if we take for V an eigenvector associated with lambda n, it's a critical point. Well, V is an eigenvector associated with lambda n. In this case, the value of the Sn for this vector V becomes 2 on lambda x2, lambda n minus lambda norm of V2, and this quantity is positive since lambda n is strictly greater than lambda. We thus see that, depending on the values of V, the sin changes sign E in the vicinity of 0, V. If the norm of V is small enough, therefore this point is not even a local extremum. It is thus a saddle point. Thank you.